So I'm Judit Angster, coming from Stuttgart, Germany. I will talk about development of innovative methods and software for the lingual organ pipe design, and I hope it is a hot topic for you. So first of all, I would like to talk about the aim of the pipe organ research, then about supporting organ builders in dimensioning reed organ pipes. I will show you measurement methods and results, computer simulation optimized with measurement results, and development of software for optimizing pipe organ sounds. So in general, the aim of the pipe organ research at the Fraunhofer in Stuttgart is to support the practical work of organ builders, because we think it is pretty important for them. Making this, we develop innovative solutions, tools, methods, and design software for them on pretty different fields like wind system, dimensioning flue pipes, dimensioning reed pipes, and so on. This time I will talk about dimensioning reed organ pipes. Just to remember how the structure of a reed or lingual organ pipe is. There is a tongue which is responsible for the sound generation. This tongue is mounted on the so-called shallot. The shallot is something like a tube with an open side. Here there is a boot, and the pipe has also a resonator. So I will show you how we work, and I will use one pipe for showing you some examples. And this pipe is called Vox Humana, which is imitating the human voice as a pipe. This pipe resonator consists of 3 sections. This is the shallot, which continues in a thin straight neck. This is a flaring section, which comes after this, and the third one is a tapering section, which has an opening at the end. So, what is our method for dimensioning reed pipes? Our method is that, first of all, we have to investigate the physics of the pipe, because we have to understand really well the physics of the pipe to be able to help organ builders in the dimensioning. So we carry out several series of measurements, and based on these measurements, we carry out computer simulation. After this, we can develop design software. So I told the first step is investigation of the physics of the reed pipes. We already made several experiments and research on different topics, like you can see here. Now I will speak about the influence of the resonator on the sound of the pipe, as this is the topic which we worked in the last time on. To understand this, I have to show some investigation results of reed oscillation, and then I will show the computer simulation based on the measurement results, and it's very important that the simulation method is combined with the measurement results. And then about the development of the design software. So, why is it necessary to make measurements, investigations on the influence of the resonator on the sound of the pipe? The experience from earlier measurements, what we have is that by reed pipes, the pitch is mostly determined by the frequency of the vibrating tongue. But it's very important that the resonator has an essential role in forming the timbre. On the other hand, the design traditions of organ builders do not exploit the capabilities of the resonator to a full capacity. And there are very different kinds of resonators, different kinds of reed pipes, and it is pretty hard for the organ builders to really use all the possibilities by the pipe sound. So I will just want to show you the measurement setup, what kind of measurements we carried out on reed pipes. So this measurement setup shows it was settled in a semi-anechoic room, and we simultaneously made a 4-channel AD measurement. One channel was the laser vibrometer, which was detecting the vibration of the tongue. One microphone, it was a probe microphone, measured the sound inside the shell-out. The second microphone measured the sound outside the resonator. And there was a pressure sensor inside the boot of the pipe. Okay, so here you can see the setup. Here is the laser vibrometer. Here is the probe microphone, and you can see on the boot we had windows so that we can measure the vibration of the tongue. Just one example of these measurements. This blue curve, the red curve, shows the reed velocity of a Vox Humana pipe, and you can see that the reed velocity is we can say a sawtooth-like function. The blue curve shows the recorded sound inside of the shell-out. How occurs this kind of sound waveform? If a gap will suddenly be opened suddenly between the tongue and the shell-out, then pressure impulse occurs and will be reflected in the shell-out back and forth. So a decaying sound signal will occur, and it happens in each vibration period. Now as I should like to talk mostly about the resonator influence, we made some resonator measurements. This you can see here the transfer function measurement, which is the ratio of the spectra measured by the probe microphone and at the open end of the resonator. So here, one of the transfer functions of the Vox Humana pipe. You can see here all the eigenresonance frequencies of the resonator together with the shell-out. You can see that the first eigenresonance frequency is by 733 Hertz. This is much higher than the sounding frequency of the pipe, which was 208 Hertz. Other measurements showed us that only a small resonator effect on reed vibration and shell-out sound happens, but as I already told, the resonator can amplify certain partials. So now we will carry out a simulation of the Vox Humana resonator, and here I have to mention that no analytical formulations are known to us that could explicitly evaluate the radiation impedance from a flaring or tapering pipe end. So the proposed approach was here a combination of the one-dimensional model of an axisymmetric resonator and the three-dimensional finite element method extended by infinite elements. So just one result of this simulation. Here you can see the waveforms at the first 4 eigenfrequencies of the Vox Humana Resonator. At the first eigenfrequency, you can see that the pressure maximum is located in the middle section of the resonator, and by the second, third, and fourth, it is located at the neck part. Now, this is a measurement for the comparison of input admittance calculated using analytical and FEM impedance models and the measured transfer function. The black curve is the measured transfer function, the red curve is the input admittance analytically simulated, and the blue is the simulation with FEM hybrid method. It can be seen better in this table what are the frequency values of the eigenresonance frequencies. And here you see the simulation result with the analytic method, and here with the analytic extended with the FEM method. You can see the error pronounced in cent is much smaller if we use the extension with the FEM methods. So we know now that this FEM modeling is necessary. And now I should like to come to the software. What is possible with the software? So here you can see the main window of the software and the most important controls. At the beginning, you can construct a resonator from different cylindrical and conical elements, like here. We need 3 different parts, but it is up to you how many parts you need, so you can construct also a pretty complicated resonator. The next step is that you can build to your resonator also a shell art. So it can also be taken into account, and here you have to add the shallot dimensions to the program. And at the end, here you can simulate the generation. For this, you can also add some data, or it is also possible that you use a real measurement result and add this function here. So now you can see the first simulation. We use a noise generation. The noise modified by the resonator can be seen here. So here you can see the eigenresonance frequencies of the resonator. A second, we use a sawtooth or sawtooth-like generation, which will be modified also by the resonator. In this case, you can see that the third partial is not the largest one, but by a Vox Humana pipe, the third partial should be the strongest one. And because of this, we use the software now to optimize the sound. So in this case, we change the dimensions of the resonator so that the conical part near to the open end has to be elongated, and in this case we find an optimal place where the first eigenresonance frequency is equal to the third partial, and because of this we have an optimal Vox Humana voice. And so I come to my summary. So our aim was dimensioning of reed organ pipes. We wanted to examine now the influence of the resonator on the sound of the pipe, different measurement methods and results have been shown. And then computer simulation was made, and it was really important to know that we always match the simulation to the measurement results, because it's really important for the practical use later. And then we developed the software for the organ builders to be able to design the pipes. As outlook, I should like to say that this extended knowledge about the pipes or of sound generation can serve as a physical model of sound synthesis. And because we have a lot of data and a lot of knowledge, our plan is for the future to develop innovative organ pipes. Now just, I hope, okay, it works. Okay, so this is the research pipe organ in my institute, which we use for the research pipe organ in our institute, which we use for testing and demonstrating all the innovative research results. Thank you for your attention.
We do have time for a few questions, if you would be willing to take questions.
Thank you for a very interesting presentation and for revisiting an almost ancient topic with new ideas. I understand that the sound of an organ pipe is very raspy if you measure it near the pipe. But if once it mixes with the reverberation of the space, it has a very smooth sound, relatively speaking, so that the room reverberation has a first order impact on the sound of the pipe. So in the example you gave here, was the sound measured in the room, so it mixed with reverberation?
No. So generally, even we make carry out the measurement in an anechoic room. This was, you couldn't see it really well, but this was a semi-anechoic room, just in a modern way. So we had only a floor, but the floor was very important because of the laser vibrometer, because it needs a very floor without any vibration. And that's why we were in this room. But we measure without any room effect, because we should like to know only the physics of the pipe and not the physics of the pipe and room common system.
So may I ask you, what in your opinion is the consequences, if any, of measuring near the pipe rather than measuring in the room itself? Do you have any comment to make about that? I can understand why it would be helpful for your design studies to measure near the pipe.
Well, of course, if we should like to find out the physics of the pipe, it is very important to make the measurement very near to the pipe. But if you are in such a room, I don't find the pipe sound raspy, so I don't think it is. It is a very clear organ pipe sound, but it is, of course, very different if you place this pipe into a reverberant room. Then you hear it like in an organ concert, and it's very different.
All right, let's thank all of our speakers again, and thank you all for coming.